Our today's speaker is Rakib, who is an integrated PhD student at TIFR in Department of Nuclear and Atomic Physics. And he does pretty interesting stuff that he takes extremely high power lasers and hits them onto target. And you apparently create some star-like conditions by successfully different. And no. I'll speak louder. So sorry for that. So please sit in front because I feel you're some hearing difficulty. We'll turn off the fans. So what they do is they take extremely high power lasers and hit them on the target and create some conditions which are almost star-like. And that's where we see this interesting title, Sitare Zameen Par. So I don't think that you're breaking stars and bringing them on soil, no. But you're creating star-like conditions in your lab and studying them. So with this, now please start your slideshare and speak loudly for the in-house audience.
Yeah. Thanks a lot. I'll just share. Good. Hello. Yes. So, hello everyone, and first of all, thank you all to come here on a Sunday morning. And yes. So, first of all, thank you for coming on a Sunday morning. And today we are going to discuss, as Ullas explained, that some very exciting stuff. And so let's start. So first of all, what do we study in the lab? So we study the fourth state of matter, which is called the plasma, right? Now, the plasma is the most abundant state of matter in the universe. So what is a plasma? First, let's understand that. So we all know about solids, right? Solid, liquid, gas, we all know. Now, what are, let's say we take some solid, and if we hit the solid up, that is, we increase the temperature of the solid, we'll get a state which is a liquid state, right? Now, if we hit the liquid up again, we'll get a state which is a gaseous state. Now, let's say we have a gas, and if we increase the temperature more, what will happen that from the atoms, the electron will start to separate out. So from the atoms, you will get a mixture of electrons and ions, okay? So you will get a positive ions and electrons. And the soup of this thing is called a plasma. So plasma is nothing but a mixture of ions and electrons, okay? Now, why should we study the plasma, right? So if we look at our universe, it's hot, dense, and the conditions that we experience, if we look at the stars, or if we look at deep down to the planets, these are the conditions that one finds. These conditions are highly dense, and the temperatures are very high. And this kind of state of matter is high energy density systems, these are called. And so these are very hard to create in earthly labs, right? So if we look at the types of plasma that are there, we can see that our sun sits somewhere here in where the densities are very high, of the order of 10 power 32 particles per meter cube. Yes.
Plasma gets charge, positive, negative. What is the condition to get charge?
No, so you have to excite the atom to separate the electrons out from the atoms. Yes, you have to add temperature, or you can create plasma by different means of techniques. So there are different techniques of creating a plasma. You can heat it up and then it will get plasma. Otherwise, you can heat lasers and it will absorb some energy and it will give you plasma. So there are different techniques. Okay. Now, if we look at the temperature and density scales, the solar core has a temperature of the order of 100 million Kelvin temperature, and densities of the order of 10 power 30 particles per meter cube. And the kind of star that we study is right up here, just near the sun. So the kind of environment that we study, the kind of uh, uh, environment that we study is very near to the solar core. Okay, so this kind of stars we create. Now, the question is, how do we create this kind of stars, right? Now, the answer is by delivering huge power into matter. Now, how do we deliver huge power into matter? Is by using some of the most powerful lasers ever built. Now, how does this lasers actually work, and how does they produce this much how high power? So the answer is simple, but not that simple. Let's see. So power we know is energy over time, right? Now, if we want to increase the power, let's say, so either we have to decrease the time to very short time, or we can do is increase the energy, right? Now, what kind of time we are talking about here? Let's see that. So if we look at the time scales that are available to us, this is where we live, and these are months, and this is the age of the universe, let's say. And if we go down, here is 1 minute. And if we go down more in milliseconds, our usual camera flash, phone camera flash, or physical camera flash, they work. And then if we go down more in tens of nanoseconds, these are where all the electronics that we use, they usually work. So our phones, our computers, they work in tens of nanoseconds. Now, to get to the light pulse that we are talking about, we have to go 6 order of magnitude from here, and what we get is tens of femtoseconds of light. Now, what is then a tens of femtoseconds light? Is a femtosecond is a millionth of a billionth of a second. Okay. Now that is 0.14 zeros followed by 1 second. Okay. So that is tiny small amount of time. And if you concentrate some photons are light particles. So if you concentrate some photons at that for particular that amount of time, you get very high powers of the order of terawatt. 1 terawatt correspond to 10 power 12 of watt. So usually whatever light we are using or fans we are using, these are, let's say, 100 watt, right? So this is terawatt, that is 10 power 12 of watt. So this is huge power. Now, in the lab, the kind of power that we create in the lab are usually order of 150 terawatt. So we have a pulse energy of 3.75 joules, and we create a femtosecond pulse, which is 25 femtoseconds. And if we calculate the power, it's around 150 terawatt. Okay. Now, if we take this laser, so this laser beam is this much big. Okay. And then if we take this big laser beam, and if we focus it to a tiny spot like of 10 micron, smaller than our hair size, then we reach intensities which are more than 10 power 19 watt per centimeter square. And we'll see how that intensity relates. So these intensities are relativistic intensities. That means the electrons inside the matter are moving relativistically. That is moving very near to the speed of light. Okay. Now, just to give you an idea what these intensities means, suppose we have a imaginary lens which is very big, size of our Earth. Okay, and with this lens, we take the full light rays of the sun that is coming to us on Earth. So the total sun rays that is coming to the Earth, we take that sun rays and we focus it to a tip of a pin. Okay. That is the energy, that is the intensity basically that we are talking here. So it is huge intensity. And in normal day-to-day life, we don't experience this. So on normal day-to-day life, whatever intensities we encounter is of very small intensities of the order of 1 watt on a fingertip. But when we have this kind of lasers, the intensity scale is very high, and the matter actually excites and the electrons oscillates, and most of the time the electrons leave the atom and forms plasma. So this is an animation where Suppose we have a gas blaster and we send this kind of laser pulses. When this comes, the matter gets ionized, and then the electrons leave the system, and then you only have the positive ions. And if you keep the positive ions together, what will happen? So everyone has a Coulomb repulsion. So everyone is positively charged. So they will repel each other. So there will be a blast. There will be an explosion. It's called a Coulomb explosion. Okay. And from that, you get accelerated particles, energetic positive ions, neutral atoms, energetic electrons, all the things. Now, before we move on, it's good to know what is a laser. Okay. Now, laser is light amplified by stimulated emission of radiation. We'll try to understand a bit of it. And lasers are very special. They are not like the usual lights that we use. So usual torch or usual lights that we use are not monochromatic, not directional. They are incoherent. But lasers are very special type. They have some very interesting properties like monochromaticity, directionality, and they are coherent. Now, what is a laser? So you need basically 4 things to make a laser. Okay, only 4 things. What do you need? So you need 2 mirrors like this, and then you need one active medium which generates the light, and then you need one more source which activates your material and gives you the light. Okay, yeah, question. What is? Sorry, I can't hear it. What is monochromatic? Monochromatic is single color, you can say. Okay, the white light that we see is a mixture of all the colors. You know about Vivgior. So Vivgior is contained in a white light. If you see a perfectly red light, then it is monochromatic. We have to see the how much color it is contained in. Okay, and if it has only one color, then that is monochromatic. Okay, in simple way. Okay, now how do you make a laser then? So you take 2 mirrors, and in between the mirrors you put one material which is called an active material, and you activate this material, you excite that material and create something known as a population inversion. So you basically take the active medium to an excited state. Okay, let's say this is the active medium. This is one atom of this active medium, and let's say this electron was here, but we somehow took it here to here. Okay, now if we send one light pulse of particular energy, what will happen? That this electron will come from here to here, and you will get 2 photons. Okay, so you send one light pulse and you get 2 light pulse back from one atom. And now these 2 light pulse goes and creates 4 light pulses, right? And those 4 goes and creates 8 light pulses, right? And that's how inside a laser, a highly intense beam of light is created. So the first laser was invented in 1960s, May 16, 1960s by Theodore Maiman. And after 60 years, lasers are everywhere, right? We experience laser in medical science, in satellites, even in militaries, right? Nowadays. So lasers are everywhere. But the sad thing is that this guy never got a Nobel Prize for inventing the laser. Okay, now, let's say we have a laser and the laser beam comes out. Now what we have to do, the usual lasers that were first built was continuous laser. Now what is a continuous laser? That if we look at the laser intensity, it is straight line. That is, for all the time, the intensity is constant of that laser. Now let's say we wanted to make it very short pulse, right? Otherwise the power will not be much. So we have to contain all the light in time. We have to make it very short. So how can we make light pulse short? Is, let's say we have some laser going in. For example, if we have this laser going in, if I put a if I put a block here, it will block remove the block, it will allow. And if I do it very quickly, I get a pulse of light, right? Now, this pulsing by this physical shutters, we can't do it better than some milliseconds. So if we want to do better, if we want to do nanoseconds, then what we can do, we can use some electro-optic crystals. There are some electro-optic crystals where if we allow voltage, it will pass the light. If we don't allow, give some voltage, it will not pass the light. That we can do in nanoseconds, and these are called nanosecond Q switching. And by those Q switching, we can create nanosecond pulses. But how do we create femtosecond pulses? So femtosecond is again 6 order of magnitude down than nanoseconds, right? So how do you go there? So by this kind of techniques, we cannot do. What we have to do is something known as mode locking. Now, what is a mode locking? Remember, I told you that for a laser, you have 2 mirrors, right? And inside these 2 mirrors, there are different frequencies that are allowed in a laser. Okay. Now you have to add them in a particular way to get a pulse like this. So if you add this kind of frequencies all together in a particular phase, they will give you a pulse. Okay, that is the basic idea. Now we have to create very high power laser. So by this technique, mode locking, you can create a very short pulse, but you cannot increase the energy, because if you want to increase the energy, you will damage your whatever optics you are using. Okay. Now, so how do you increase the energy then? So there is a technique called chirp pulse amplification, which was invented in 1980s by these 2 scientists, Gerard Morrow and Donald Strickland, and they got Nobel Prize in 2018 for that discovery. What was the discovery? Their idea was simple. Okay, so I get a very small pulse of light, but with very low energy. Okay. How do we increase the energy is, first let's stretch the pulse. So in time they stretch the pulse, so the power will be less because now you have stretched, right? And then you increase the power by something known as amplifier. So you increase the energy contained in the pulse. So you increase the energy, and in the final stage you compress the pulse back. Okay, whatever we have stretched here, we compress it here. So now the pulse is compressed and the energy is more. Now you take this beam and do your experiments. Okay. So this is a laser in our lab. So this is a 20 terawatt laser. You can see some part of it. And this is a 150 terawatt laser at TFR. This laser occupies a whole big room like this. And so this is the laser room. This is as big as this hall. And this is the experimental chamber where we do all the experiments. Okay. Now, the question is, can we create a star kind of matter? Now, to create a star kind of matter, that means we have to reach extremely high density and extremely high temperature. Now, what are the conditions inside the sun? Is 100 million Kelvin temperature inside. Pressures are of gigabars and densities are 1,000 times larger than that of water, and very high magnetic field. Yes.
We determine how much power and for how much time you want to create that power.
Yes.
So you are in the earlier step. 1 more second.
Yes.
Yeah.
So let's say here.
So what you do is start with the narrow beam.
Yes, narrow beam. Yeah.
Narrow beam. You stretch it.
You stretch it. So the thing is, whatever beam you create here, you cannot reach here better than that in time. So that is always your constant. Right now, there are like developments in how you can decrease the beam size than this. So people are also trying that, but fundamentally, I mean, you can roughly get the similar kind of pulse, temporal pulse, whatever you have made earlier. And the energy you can increase. There are limits where the mirrors can get damaged, but other than that, you can. So for example, you can increase the power of the beam as you want, as long as you are in the safe limit. Okay. So the thing is, Yes. You can only go in steps. It's not continuous. You can only go in steps. So to increase the power, you need to apply more and more other lasers to increase the power of this laser, basically. So we use different kind of other lasers to increase the energy in this laser. So those are your constraints to how much you can add and what you can do. Yeah. Yes. Yes. Because if you don't stretch, if you want to increase the energy from here to here, what can happen that from here to here, the increase is like 10.9 times. Okay. So when you increase the power from here to here 10.9 times, what can happen that suppose so inside the laser, there are mirrors, there are other optics, right? There are crystals. What can happen that your optics and your mirrors can get damaged. So to reduce the damage, you decrease the power to be safe. Yeah. Okay. Now, inside the stars, these are the conditions. Now, the star is powered by something known as nuclear fusion. So what happens in a nuclear fusion is you take a deuterium and a tritium and fuse it to form a helium and one neutron with very high energy. And this energy is if this energy is extracted, then we can make what is known as the safest energy plant of in the earth. Okay, so this is the process that is going inside the stars, and that basically powers the stars, right? The nuclear fusion. Now, can we do fusion on earth? So there is one project going on in National Ignition Facility, which is in LLNL, USA, where they take 192 laser beams, very high energetic laser beams, and they focus it on a 2 mm round bead. So the target is 2 mm, like this much big ball, and they all take the 192 laser beam comes and hit this ball from different directions. Okay, so let's see one video of this. So as you can see, this red thing is the laser beam going in, and there are 192 lasers total that comes, and all the laser beams goes, and all the laser beams are designed such that they all reach the target at the same time. Okay, so you can see all the laser beams going in, and then in here you have the target. So they goes in and they get focused onto a target. So see here, this is the target, and then all the laser beams hit the target, and they try to create a fusion inside. Okay, this is one of the biggest project that is going on, and you can see these videos. If you go to this website of National Ignition Facility, LLNL, you can see more of these videos. Now, how this high energy density is created in by this ultrafast lasers? So the idea is very simple. You have to hit the electrons so hard that the electrons gets heated up very fast, and then the electrons leave the system, leaving the ions there. So the density that we see in of everything is basically of that of ions. Okay, so the ions remains frozen, so the density is there, and then you have very high temperature in the electrons. And why doesn't the ions then react? Because ions are heavy, so electrons are very light particles, so they interact with light very much. But the ions, so if you take, let's say, proton, so proton is 2000 times heavier than electron. Okay, now if you have, let's say, whatever you have, let's say carbon atom, so you have six electrons, 6 protons and 6 neutrons, so that is roughly 24 times 24,000 times heavier, the nucleus is than that of electrons, right? So that is very heavy. So moving a heavy object is very difficult, as we see also in real life, right? So the ions react very slowly. So when the laser is there, the ions doesn't react. Only the electrons that reacts, and after the laser pulse is gone, the ions start to react in picoseconds, and after picoseconds, the ions start to move very slowly. Now, with this kind of lasers, you can do what is known as laboratory astrophysics. So you can study not every aspect of astrophysics, but some of it. Okay. You can study accelerator physics. So I'll discuss that we can generate very high energetic particles from this kind of lasers. So with those, you can basically accelerate protons and electrons and use them as an accelerator facility. And you can study what is known as warm condensed matter physics and particle physics. Now, these were the overview of the whole subject. Now, I'll discuss what we usually study in our TFR. Yes. What is? I didn't understand.
Can you move it?
This one? Here? Here? Okay. I'll discuss all this. Okay. I'll discuss all. So here I'll discuss. Okay. So in TFR, what we do is we have this laser which we focus on a target. So this is a target, and when we hit it with the laser, there are like very high energetic particles like electrons, protons, and neutral atoms. They come out from the interaction point, and then there are X-rays, gamma rays, higher harmonics, and all sorts of radiations that come out. And you also have very high magnetic field in the vicinity of the interaction point, because all the charged particles are moving. So you have very high current and so very high magnetic field. Yes. HEG is higher harmonic generation. Higher harmonics are, let's say you have a laser which is 800 nanometer. So you can create frequency doubled, meaning you can create 400 nanometer light, 200 nanometer light, 100 nanometer light, 50 nanometer light, always half if you go. Then these are called higher harmonics. Okay, that means they are of similar kind, but the frequencies are doubled, tripled, 5 times, 6 times, 10 times, right? Like this. Okay, now I just want to give you a flavor of what happens in the lab. So, okay, if you can hear, so you see here, there is some spark, right? And the spark is when we focus this laser on air, the air gets ionized and creates this plasma. And then you can see different colors of light come out from here. Okay. Now the light that we send is actually a red light, only a red light. Okay. But the light that comes out, you can see all the colors here. You can see red, you can see yellow, you can see blue, you can see green, right? From all the things. So these are because of some nonlinear optics that is going on in the air. Okay. And here we will see how when we discussed here, that when we hit the laser on a solid target. Okay. So let's see this video. So the laser comes, hits, and releases this all sorts of radiations and this high energetic particles. Okay.
Are these the real time?
Yes, these are videos taken from our lab. I mean, I have taken those things. So this is real. Now, what do we study in the lab? So we study many things, like we study what is the energy of the electrons, how the electrons are distributed in space, how the protons are distributed, how the magnetic fields looks like inside, what kind of magnetic field that we create inside. And we also want to see how, so when we create this plasma, sorry. So when we create this plasma, so the laser comes, it creates the plasma, it becomes very hot, right? And then the laser goes, because the laser stays for a very short time, the laser goes, but the plasma is there and it is very hot. So any hot thing will try to explode, right? So the plasma explodes, it comes outside to the vacuum, and then it explodes, and within 50 picoseconds, 60 picoseconds, the plasma eventually dies out. Okay. Now we wanted to see how this plasma looks actually in real time. So these plasmas that we create are in very small space and in very short time. So the plasmas only live for let's say hundreds of picoseconds. But how do you see hundreds of picoseconds? Because no cameras, no electronics can work in picoseconds. Okay, all the devices that we know, they usually operate in nanoseconds. So how do you see? So we'll see how we so we wanted to see the plasma evolution. And inside the plasma, there is one layer called a critical layer, where the light reflects. So suppose you have the plasma which is expanding like this, and then if you send one light pulse, it cannot go through it. So from some point it will get reflected from that particular layer. So that particular layer is called a critical layer. So don't bother about the equations, just physical thing. And that from that critical layer, why it is critical? Because it is the most important layer inside the plasma, because all the high energy particles and this radiations, they mostly come from that layer. Okay. So understanding that is very important, and this critical layer reflects the light. That is the most important thing we have to understand. Now there are many studies of how we see these plasmas. There are some studies from all over the world and also from TFR, but most of them are indirect measurement, in the sense that you don't really see the plasma, so you measure some parameters, and from that you infer that okay, the thing is going like this. Okay. Now in my PhD I have this question, that can we take real-time photos of the raging and aging of the plasma? So raging because it is evolving, so it is very high temperature, so it is exploding, and aging because eventually the plasma dies out. Okay, so can we see these things? It turns out that we can, and by measuring the reflected light from the plasma, and we look at a particular phenomena of the light that is reflected, what we call the wavefront. Now let's slightly understand what a wavefront is. So every day we encounter some waves, right? Let's say the sun outside. So from the sun, the waves are coming, and then we are seeing it here, right? And by the time the wave comes to Earth, the wavefronts are almost flat. Now, what are wavefronts? Wavefronts are the surface that is defined by the points of same phase, right? Now, waves can be in several types. So one is the light wave, one can be of the waves at TFR seesaw, no, and other types. So how do you measure this wavefront of the light? Now wavefronts can be different types, like planar wavefront and converging wavefront, diverging wavefront. So let's say if we take a lens, and if we take a planar wavefront, let's say the sunlight. So if we take a magnifying glass and put it in a sunlight, what will it do? It will focus the light, right, at a particular point. And there the wavefronts becomes curved like this, and it gets converged at the focus. After the focus, it again diverges. Now the question is, can we measure these wavefronts, the curvature of these wavefronts, how it looks? The answer is yes. So there are like different techniques by which you can measure this. There are several techniques, but I'll just give you one or two. Let's say we take a array of small size holes, and in those holes we put some small lenses. Okay. Now if we send some light pulse, let's say light, and then because of these lenses, it will focus at different points, right? Now at the focal plane, if we put a CCD and if we record where it is focusing, it looks, I mean, it turns out that we can reconstruct what the wavefront was. Okay. There are other types of measurement of wavefront by generating different copies of the beam with a grating and a phase plate. Let's say we have one beam, then we can create, let's say, 4 copies of one beam and see where they are interfering, and we record one interference pattern, and from that it also turns out that you can see how the wavefront looks. Okay, now that is wavefront measurement. Now we have to see how the plasma is evolving. Okay, now as I said that the plasmas are evolving in very rapid time. So how do we see it? So we can't see it with any electronics or anything. So the answer is with a technique called a pump probe technique. Now, what is a pump probe technique? Now remember that I said that plasma always reflects light from inside one layer. Idea is that, so we are creating the plasma with a big laser, right? So this is a big laser, comes and creates the plasma. Now what you do is we send some small part of this laser, which doesn't make the plasma very unstable. It just goes, touches the plasma and comes back. Okay. So it goes, touches the plasma and comes back. And we look at what comes back. We put a detector and we see different properties of it. Okay. This technique is called a pump probe technique. So the main laser that comes, that is called as a pump pulse. So that creates the plasma, and a small part is a very weak pulse that comes, sees the plasma and goes back. It's called a probe pulse. Okay. Now with this pump probe technique, what we can do, we can delay how much. So let's say this guy comes first, and then so let's say there are 2 runners. Okay. So one guy goes first and does something at the end point. I send another guy from here, and he goes and sees what he does. Okay. Now the second guy, I can send the second guy at whenever time I want. So that's how I control this pulse. I send this pulse at different times to see how the plasma is at different time. Okay. Now this is a small animation of how things look. So the main pulse goes, creates this plasma, and the second pulse goes, if you see, the second pulse goes and sees the plasma and goes back, and we study that one. This is our setup where, so we send this pump pulse here, we focus it at this point, and then the second pulse goes, sees the plasma at the same point at after some time, and then it comes back to our detector. Okay. Now the idea is very simple. Idea is that the second pulse that we send, that is bigger than the small. So this was the pulse that was creating the plasma here. The second pulse is much bigger in space. Okay. So some part of it sees the plasma, some part it doesn't see the plasma. Okay. So the part that sees the plasma comes and it reflects from outside layer, right? The layer we discussed, the critical layer. And the other part which doesn't go through the plasma, so it reflects from the target surface and comes back. So this guy comes first, this guy comes second. So if we know the difference between this and this, we can reconstruct how this looks. Okay. So that is the idea. And we have some calculations by which we can calculate, but this is the important result, that if we come after some time, we see that the plasma is actually expanding like this. So this is the real-time surface of the plasma, how it looks. Okay. So you can see that at the center part, this is evolving. So this is where the plasma was not created. Here the plasma was created, and here the plasma is expanding, right? Yes. Sorry. So these are at different times. So I send the guy at different time, and different time I see the plasma. This was one idea. Okay, now, so this was the main interaction that was happening. Now, if we look very closely inside here, what the electrons are doing when the pulse is there, the electrons are doing this kind of motion. Okay, so this is called a figure of 8 motion. So the electrons dances like this. Now, if we have a high power laser and which has a non-uniform electric field, the electrons will start to shift like this. It will not just stay here and do this figure of 8 thing. It will start to move this way because of the light pressure. Okay, that is, the light pressure is called a Ponto-motive force. That is higher order concept. But simply we can understand that suppose you have a plasma and a light. So any radiation has a pressure, and the radiation pressure is given by I by C, right? Now, due to this light, the plasma surface will get pushed, right? And plasma surface will get curved like this. Now, we want to measure this curvature. So that is the curvature made by the light itself. So curvature made by a wind we have seen, right? If we have some big cloth, we can see when the wind is flowing, the cloth is curved, right? Like this. Now, this is a curved surface by a light. So the surface gets curved like this, and this has been predicted from 1980s, 1990s, and they have seen all these things from calculations. Okay, so these are from calculations, and we wanted to measure this. So this is our setup. When we send the laser, we create the plasma, and from the plasma we reflect the laser and take it to our detector. And when it goes to the detector, you see that the light has actually bent the surface like this. So you see, so when we increase the intensity of the input light, you can see the surface is more and more curved. Okay, so this is a very interesting result that we have got recently, and we can calculate how much the deformation is, and we try to model it with some. So this is the summary that that we have discussed. So we have discussed about lasers, and we have discussed about some very high power lasers that are available these days, and about intense laser matter interaction, and some of our TFR work, not all of it. So you can take a photo of these keywords to read some of our works. And this is the website of our laboratory. You can just scan this QR code to reach our webpage. Yes. Right. I'll discuss. Okay.
Basically, on this note, I think you're finished.
No, I have 1-2 slides more.
So
Okay.
it looks like you're stopped.
Yeah. So we also have a student outreach named TFR Optica Society. We also organize some outreach programs at Marine Drive or some places. You can follow us on Instagram by this QR code. And this is our team at Afil. So our lab is called Afil, and this is us doing exciting things. One of them is here, and yeah. Thank you all for coming here on a Sunday. Now, coming to your question. Yes. So the question is, throughout so my main work of my PhD was to study how this surface gets curved and how does this surface looks. And the question is, why do you want to study this? Okay. What is the motivation of this? Okay. Now, as I discussed that the critical layer that we have said is a very important layer, because that is the point where all the action is happening, right? That is the point where so that is the point from where this high energetic particles are coming in and higher order harmonics are generated. So higher order harmonics are also So you know about higher order harmonics. So these are, let's say I have some 800 nanometer laser. So it has a frequency corresponding to it, right? And what can happen in any nonlinear material is that you can create the double of that frequency. Let's say I have some omega frequency. You can create a 2 omega frequency. You can create a 3 omega frequency, 5 omega frequency. So people have created this many frequencies. These are called higher order harmonics. And from that, people have created what is known as the shortest event on Earth. What is basically awarded the Nobel Prize last year is the attosecond pulses. You have heard about attosecond pulses. So right now we have talked about femtosecond pulses, which are 10 power minus 15 seconds. Okay. Now attosecond is 1,000 times smaller than this. Okay. Now this attosecond pulses are actually created from this layer, the vibration of this layer, and how the attosecond pulse goes and what is the properties of this attosecond pulse depend on how this critical surface looks. And now this attosecond pulses are very much in use of seeing the real electrons moving, because earlier we didn't use to see the electrons inside the atoms. Now these attosecond pulses are being used to see the motion of the electrons. These are so short that it can capture the motion of the electrons. So for this kind of things, this is very important to know. Okay. And the most important thing is that this is where all the action happens. So you should fundamentally understand how this surface looks at different times so that you get the physical idea. So that was the motivation of my my PhD. Yes.
What we do is we'll stop the online part.
Yes.
Take a break.
Yes.
Okay, and ask questions here.
Yeah.
Okay. So with this, we stop only the online part. That's so. Let's thank Rakil. And probably it was very fast and very intense. And I guess there are lots of questions, and you'll have to tell the kids what is Sitara and how are you again doing. Right?
Sure.
They are interested. All right. So.
Yeah.